Now in exercise 11b, we are going to use this fundamental theorem of calculus. It doesn't really matter that that's what it's called, but we're going to use that to actually evaluate our integral. So you know that when we differentiate, we got an expression for the gradient, and then we evaluated the gradient. We got a value for the gradient. That we're going to see a similar process here. Well, you've seen the process of finding the primitive function or integrating. Now we're actually going to find a value, and we're going to measure the actual integral. Remember I said for us to be able to do that, we have to define the limits of our integral. Where are we going to start and where are we going to finish? And so it makes sense that we will call these integrals definite integrals. So according to the fundamental theorem, if we want to find the integral from, this is where we will start, and B is where we finish. We want to find the integral from A to B of a function. Then we must find the primitive function, as it says here, the primitive of our f of x. And when we've done that, then we evaluate. We're going to substitute x for b. So we put our finishing position value for x into our primitive function, and we subtract, substituting our starting x value into our primitive function. Let's have a look at some examples. It says find the area under the curve of 3x squared from x equal 1 to 2. So you could have a bit of an idea of what that actually looks like. 3x squared we know is a fairly skinny-ish parabola, and we are finding the area under this curve, so we're getting the value of the area of this section. So that's graphically what we are doing, and you'll find that with integration it's critical that you can draw the graphs of your functions. So that's graphically our graphical representation of what we're doing. Algebraically, I want the integral from 1 to 2. And my function is 3x squared, and I'm integrating with respect to x. Now, the actual notation is, well, hang on, we'll find the primitive function first. So our primitive function would simply be x cubed. Now, we don't put plus c, and I'll show you very quickly why. We know that if we actually had our x cubed, if x cubed is the primitive, so let's say we've got subbing in 2, because that's what the fundamental theorem says. So we want 2 cubed. If we kept our constant in, 2 cubed plus a constant, then we have to subtract subbing a in, which is our 1 cubed plus a constant. So we've got to subtract all of that. Then we would have 2 cubed plus a constant minus 1 cubed, and a minus times a positive is a minus. c, plus c minus c, the constants disappear. This happens every time, and that's the reason why we don't include the constant. We won't ever need to include the constant on a definite integral. Our first step is to indicate that we're going to, we haven't yet substituted our 2 in the place for x. Now, we introduce another type of notation. We no longer say we're integrating, because I'm not now integrating, I've actually integrated. I've added 1 to the index and I've divided by the new index. However, I need to indicate that I still have more steps in the process, and that is where I'm going to substitute, or I want to find the value of this from 1 to 2. On my next line, I do that. I substitute x equal to 2. So we've got 2 cubed, and the fundamental theorem has a minus here, which causes us some grief at times, because if I hadn't bracketed this, then I may not be subtracting all of the second function with the a substitution, and I would have the wrong answer. If I don't subtract every item in that function, then I've got the wrong answer. So the minus is, like I said, causes some grief at times. So sub the 2 in, now sub the 1 in. 2 cubed is 8, 1 cubed is 1, and we say it's 7 units squared because we're finding the area. Now you can see there I've also written, don't forget your graphical understanding for these questions. Can't emphasize that enough, because, always we try to relate between the graphical representation and the algebraic form. And it just gives us another dimension to our understanding. There will be some times later where you won't be able to answer the question unless you've drawn the graph. So, you'll see how important it is that you can think about the graph and relate it to your algebraic process. Okay, let's have a look at this next example. So it says, evaluate, find the value of the integral from -5 to -3 of -3x. Now over here I've said, describe in words what this is finding. So what this is actually finding is the area under, and it's actually not a curve, it's a straight line. -3x is a straight line. Goes through here because when x is 0, y is 0, and it's got a slope of -3. So this is our function in x is -3x. Now what are we actually finding? We're finding the area under this from, let's go -1, -2, -3, -4, -5. We're finding the area under this curve from -5 to -3. We're actually finding this area. Now, in this case, we could actually do it by finding the area of the trapezium because the function is a straight line. However, we're not going to do it that way. We're going to use our calculus. So, I've written the question. This should have a dx in there. This function is in the format such that we can integrate, which is add 1 to the index, divide by the new index, and you can see I've done that. -3, add 1 to this index, becomes a 2, divide by the new index. Now that I've found the primitive function, I'm indicating here that I'm going to evaluate it eventually from the limit -5 to -3. The rule says that we put the second value, or the value to the right-hand side, in first. So we're subbing x equal to -3. Now please take care, it doesn't matter how many lines of working it takes. I would be using as many lines of working that I require to ensure I'm careful and getting the correct answer. So I'm going to show the substitution of -3 being squared all over 2 and with a -3 at the front. Subtract, because that is the rule. Again, it's -3 times, and I'm going to show the -5 being substituted for the x. That all has to be squared, and it's over 2. So it is -3 times 9 on 2, subtract. It doesn't matter when I deal with this. It's -3 times 25 on 2. 3 9's -27. And we've got a negative and a negative, which is a positive. 75, which is 48. 48 on 2. And 48 on 2 is 24 units squared. So this area, the shaded area under there, would be 24 units squared. I'll stop the video there and put the solutions to the next ones just on the OneNote, and I won't do a video, I'll just show you the solutions.